Okay, so as the title suggests, this is the third of these marine ice sheet model comparison exercises, and the previous two have been run by Christian and Richard Highmarsh and by Frank Pattyn, and Hilmar and I have been volunteered to run the third. And like the previous two, the focus of it is on grounding line migration in marine terminated ice sheets. So, well, at least I think the motivation for doing these things is something along the lines of you need precision for accuracy when you're trying to do ice sheet dynamics. And what I mean here is that there isn't really a way of calculating the collapse of, say, West Antarctica without doing the details, without doing Pine Island Glacier right, and without doing Thwaites Glacier right, and all those sorts of things, because at every point in time, all of the dynamics is in a fairly fine boundary layer. So, okay, the smart way, well, not necessarily the smart way, but the most desirable way to do this would be to use entire Stokes models like Elmer Ice. Typically, I think they need resolutions better than a kilometre, and when they do use that sort of resolution, it's hard to do something much bigger than Pine Island Glacier for much longer than 50 years. I'm not saying it's impossible, but that's a typical sort of application. So then you move on to models that do some vertical integration. They're simpler to solve. You can still use high resolution, and then you can do longer timescale integration. So in this example here, I'm doing vertical integrated model, and it's going for about 1,000 years. But nonetheless, you still quite often want to do longer timescale experiments than that, and also quite often ensembles and so on. And in that case, people tend to use much coarser resolution models or flow law models or something like that. And because of this issue with the boundary layer around the grounding line, and because there's something similar going on in shear margins as well, they also need to be quite finely resolved, then methods of this class need to be quite clever. And what we've wanted in the past and what we want in the future is some sort of experiment in which we can test the performance of these and these against these. So it's like, so everyone has their sort of like pet version of why precision is needed. This is the one I usually go on about. These two simulations are Antarctica is subjected to exactly the same forcing. It's extremely heavy melt rates. The top forcing has a best resolution of about 500 metres and mostly 1 kilometres around the coast, down to 8 kilometres in the interior. And in this case, Pine Island Glacier collapses, it merges with Rutford Ice Stream, Thwaites Glacier collapses, all sorts of action goes on, and you end up with a sort of net sea level rise of about 6 millimetres a year over the time period of the run. Do the same calculation at 8 kilometres, you do see something going on. So, for example, you're seeing some retreat here in the Filchner-Ronnie Ice Shelf, the Muller and Institute streams retreat, less so than in this case, but qualitatively the behaviour is right. You'd probably be quite happy with that result. Same is true on the Cycle coast. But Pine Island Glacier and Thwaites remain where they are. So you get a qualitatively different result, and the volume above flotation loss in this one is essentially reaches a steady state pretty much straight away. So it's not so much that you can, this doesn't give you a sort of rough picture of that, it gives you a completely different picture. So the design, we agreed what the design requirements were at the last EGU, and my recollection of them was that we were going to have an idealised geometry because we found when we tried comparing models on real DEMs, then the extra complexity confuses us entirely. The test ought to be about ice shelf ablation through melting and the resulting loss of buttressing, because that's the mechanism that the earlier MISMIPs didn't test, and it's one of the mechanisms we're probably most interested in. That's not to say we're not interested in the mechanism of the previous ones. And something else, the response to the perturbation we see needs to be larger than the differences in conditions. So one of the things that turned out to be the case in the last exercise in MISMIP 3D, the steady state grounding lines from, say, the Stokes models and the shallow shelf models were separated by about order of 100 kilometres. It was about 80 kilometres. But the response to the perturbation that was applied to them was of the order of 10 or 20 kilometres. So the difference between the Stokes model never advanced as far as the steady state of the shallow shelf approximation, even when it was perturbed at the maximum. So it was difficult to interpret some of the results of that. It meant we couldn't say whether some of the differences between the transient response in the shallow shelf approximation were due to differences in the shallow shelf approximation, or merely differences in their steady state because it had a much bigger ice sheet. The other reason is that it's quite typical now to try and simulate future change in these glaciers by taking observed geometries, doing an inverse problem to find basal tractions and so on, and then starting out from that state. So that means that you tend, whatever approximation you use, to start out with a state that looks rather similar. You can get much the same velocities in the shallow shelf as in the Stokes, but whether the ultimate dynamics is the same is not clear. And we also want the test to be clear about whether something is under-resolved, because we know it's important, and we want to test these kind of relatively clever coarse grid schemes that will hopefully avoid the hammer of high resolution. So the geometry we're proposing is based on Hilmar's paper from 2013. This is a central channel, and the bedrock has this downslope, upslope, downslope feature that's characteristic. Well, it actually comes from the first MISMIP exercise. And the notable feature about this is once we have these taut channels in, we find that we can get steady states on the upslope. So we know that there must be some buttressing going on there, because without buttressing, there can be no steady state on that upslope. And we solved we realized one of the design criteria straight away, because it turned out that these two models, the one we call the SSA star, which is shallow shelf approximation, but with a sort of softening in the viscosity around the grounding line, or rather in areas where there are steep slopes. They're rather close, so I can't actually make it out at all now. I can make it out on the originals, but there's a red line, which is the shallow shelf approximation, and there's a black line, which is the shallow shelf star, and they're pretty much overlying each other. One is a little behind the other. But they bracketed the high-resolution models before, so they were separated originally by 80 or more kilometres. So we hope that the geometry alone will mean that most of our problems will start out close together. It remains to be seen if the Stokes models will still be bracketed by those, or whether they'll lie some distance from them. I don't want to bet. So those are just the equations. They're just there in case anyone picks up the slides. So the perturbation we want to have is a melt rate, and to decide what that should be, I went and asked some ocean modelers. So Zylar S.A. Davis very kindly took our steady state geometry, and he ran the pop ocean model to compute a circulation in that and a melt rate. So you can see it has two characteristic features, one of which we're going to ignore to begin with, and one of which we're going to take notice of. The melt rate's rather peaked by the grounding line, and it gets up to about 100 metres per year. It's also rather peaked on this boundary of the wall because of the Coriolis force, and we'll ignore that fact for now. So Ben Felty, another oceanographer, has kindly come up with a depth-dependent melt rate that gives us roughly this sort of behaviour. And that's the equation for that. I don't want to dwell on it very long, but it's basically it's dependent on the draft, the ice shelf draft, and the water depth, and it's essentially a quadratic in that. So you get melt rates that peak near the grounding line, or peak, yeah. But I'll zero at the grounding line because of this scaling here. So here's what happens when you apply such a melt rate to the RCA. So if this is, I've picked this, there's a scaling parameter in there which allows us to choose a peak melt rate essentially. And in this case, it's around 100 metres per year. I apply that melt rate for 100 a year, and the grounding line retreats from here to somewhere over here. So it's about over 100 kilometres. And then when you turn off the melt, it starts to advance again. But you'll notice that the speed at which it advances is much slower than the speed at which it retreated. So it's going to be difficult to do a reverse experiment. So MISMIP 3D, I think one of the main things that people wanted to achieve in that was to be able to get back to their steady state after the perturbation. Now, if you wanted to do that properly, you actually had to run that model for many thousands of years to get there, but it got a good long way to the answer within a century. That's not the case here. So I think that sort of reverse experiment isn't going to work for us if we want the more expensive models to participate. I'll come back to that in a minute. So the other issue is one of resolution. This is an experiment where I've taken the shallow shelf star steady state solution and spun up at a fairly high resolution. And then I've interpolated it onto coarser resolution meshes and applied the melt rate. And the notable thing here is that at 4 kilometres resolution, despite the complete loss of the ice shelf, the grounding line hasn't gone anywhere at all. Okay, so you can see these sort of like cluster of bright lines where it hasn't moved. But as soon as I move to better resolutions, then that behaviour goes away. So at 2 kilometres, I'm getting a good deal of retreat, and as I move to higher and higher resolutions, I get a decent asymptotic convergence of that. So the 100-kilometre result is robust. But you do, if you've got a conventional type of discretization, need a reasonably high resolution. Now, that's not to say that someone won't have a cleverer method of getting around that. That's one of the things really I want to see most. So I think this is going to be the main experiment. Start out at a steady state. That could be either taking one of the steady, or we'll make the steady states that we've spun up available. So if you've got an expensive model, you could take those and maybe do a short spin up. So this is just a sort of 10-year relaxation period here to show that you're in steady state or close to it. You apply the perturbation for 100 years and then turn it off. And what you can see is over the 100 years after the perturbation's been turned off, there's a decay towards a zero gradient of volume above flotation. So that's the thing I think we want to look out for as the reversibility test. Do you get the right rate here? And it seems to me that it's worth doing it at a few melt rates just to show that this rate should be preserved across all of them. So I mentioned that I was ignoring the asymmetry. I thought it would also be worth taking that into account. So you can introduce an asymmetry into the previous melt rate law by adding a fairly simple scaling, which apparently is funny. The idea here is perhaps this isn't really going anywhere, but I thought it would be worth seeing first how easy is it to resolve these increasingly high melt features that tend to appear in real ocean models near the walls. And the second is, how much does the asymmetry in the melt rate matter to the dynamic response? And for me, it doesn't really matter at all. I can make it as asymmetric as I like, and I get pretty much symmetric retreat along the grounding line. But I don't know if that's a universal property or whether it's just a mistake in my work. So, in conclusion, we've got an experiment. We've called it MISMIT. We couldn't call it MISMIT 3 because there was a MISMIT 3 and MISMIT 1. So we're basing it on Hilmar's channel geometry with a buttress steady-state grounding line. We've got a simple formula for melt rate perturbation. It doesn't depend on anything that's going to be difficult to compute for anybody. It's just local properties. It roughly agrees with the pop ocean model, which we're going to extend this geometry to use in a coupled ice sheet ocean experiment as well somewhere down the line. You're going to need to be able to cope with about 100 kilometres of grounding line retreat, so by whichever means that's coped with. So it'll be compatible with this subshelf circulation experiment called ISOMIT, which I guess stands for the Ice Shelf Ocean Model Intercomparison Project, and then there's going to be a coupled model intercomparison somewhere down the line as well. And for conventional methods, I think you need a resolution of about 1 kilometre. And we'll announce in the new year on Cryosphere what we plan to do, and there'll be an opportunity for people who think it's a terrible idea to tell us. Thank you. Yeah, I'm meaning to tell me it's a terrible idea now.
Any questions for Steph?
In good humor, I want to say I'm deeply alarmed by this intercomparison experiment because the oceanography is so terrible, I think, that you're going to end up tuning your models to what is effectively noise in the pop ocean model. The pop ocean model is using noise to, instead of potential vorticity conservation, to drive heat under those ice shelves.
Okay, well, we're not using the pop ocean model to do this exercise. And I guess we'll see whether pop.
Why do it at all unless we have solid oceanography?
Well, that's a good question. I guess we're interested in the mechanical response to ice shelf ablation, and we know that happens in certain patterns. That we know that tends to be melt rates tend to be higher near the ground line and so on. So I think, yeah, it's true that it would be better.
Not all ablations are the same, though. And if you choose the wrong one to tune the models to, you could be actually doing worse in the model development scheme, going backwards rather than forwards.
I guess that's true. Yeah. I don't know how to resolve that.
Said in good humor.
Okay.